Okay, so these are the combination notes. Basically, what the combination notes are saying, they're combining everything that we've just learned just as a, here we go, this is all of it. So recall that the geometric series looks like this. You got A plus AUR plus AR squared with a ratio R that is in common with each one, and then you have the initial A value that starts off with n equals 0. And that converges to a sum of A over 1 minus R if our common ratio is less than 1. And if it diverges if our common ratio is greater than or equal to 1. So if it converges, we can find our R, or our interval of convergence, by using this little equation and solving it. So like we did kind of today in class. So basically the idea is for the base function. So here's our base function. Between -1 and 1, okay, you notice that the function, the base, and its series, they converge between -1 and 1. Now this is not a perfect picture, but they do. They are basically the same function in between that section. And if they are starting to separate a little bit, you know, that's fine. They are still converging towards a special number, but then later on it actually splits up completely to a whole nother function. So here is the zoomed out picture between -3 and 3. You notice that they are obviously not the same function. So they only converged between -1 and 1. That's why it's called the interval of convergence. Okay, so this is between -1 and 1. Okay, and actually it's not like exactly, because you can have a convergence factor that is close, but of course as soon as it starts becoming completely different, then it's wrong. So since 1 plus x squared plus blah 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 gives us this sigma notation is the geometric series with a equals 1 and r equals x, then this series converges to the sum of 1 over 1 minus x. Therefore, this is the interval of convergence for this special series. So basically, our r is x. So what do you observe as you compare the function with its power series approximation, f of 2, in terms of the interval of convergence? Our interval of convergence for this was -1 to 1, and the function 1 over 1 minus x and the series 1 plus x squared plus x cubed, so on and so on, are almost the same, except for at the, I'm not even showing you what I'm writing. At the end of the intervals, of the interval, near -1 and 1. That's a 1. So basically, they are almost the same except close to the end of the interval. So at the end of the interval, we're still going to include that in our interval of convergence, but we have to understand that that's when it starts to kind of separate. Okay? All right, second page. Extend this idea for a variety of functions. So if we write a power series in this form, a plus a f of x plus a f of x squared, we end up with a times f of x. This is supposed to look like that. Then this series converges to the sum a over 1 minus r by replacing that r with whatever our f of x is. But this can only happen if the absolute value of f of x is greater than 1. And to figure this out, we need to use this setup for the interval of convergence and see and simplify, if we have to get our r, what we did in class today. Okay? For the series, but we must manipulate this algebraically, getting x by itself. So when we get x by itself, then we know what our r is. So here's our example. Let's consider 1 over 1 plus 3x. So let's rewrite this to figure out, we want to figure out what our interval of convergence is and where the series converges to. Okay, so first off, we're going to rewrite this using our base. So this becomes 1 over 1 minus negative 3x, right? Because our base, remember, our base looks like this, 1 over 1 minus x. So I want to get it to look like this, because if I can, then I can say that this is equal to this, and so on. Alright, so once I've rewritten that, now basically this guy right here is going to be called my f of x. So my power series for sorry, this is supposed to be 1 over 1 plus x. Sorry about that. Okay, so my power series is going to be, remember, the power series for the base, 1 over 1 plus x, is equal to 1 plus x squared, so on and so on, and we get the sigma notation x to the n. So now for this function, which is equal to 1 over 1 minus negative 3x, what am I doing to all the x's? What am I doing to all of the x's? I'm going to replace them with a negative 3x. So this is going to be 1 plus negative 3x plus negative 3x squared, and so on. So we get a sigma notation, n equals 0 to infinity, of just negative 3x to the n. Now remember, because it was a negative, technically we can rewrite this, or we should have written it the way we have been normally, but it's negative 1 to the n, 3x to the n. It's the same thing. So this and this are the same exact thing. So here, what is our function that is raised to the n, or our r value? Well, we got to figure out what our interval of convergence is using our function, our r value. So here r is negative 3x, so we're going to set it to get x by itself and figure out our interval of convergence. We're going to set this in between negative 1 and 1, and we're going to solve. So we're going to divide everything by negative 3. So we get 1/3 x negative 1/3. But what happens when you divide by a negative? Oh my gosh, I almost forgot. These guys do what? They flip. So that means that right there is my interval of convergence. But just to leave it in, notation that we're used to, I'm just basically going to flip these around, and I'm going to say, all right, it's negative 1/3 to x to 1/3. So my interval of convergence is between negative 1/3 and 1/3. And actually, if you look at the function of these two, what do you observe as you compare the two graphs? The interval of convergence for the base shows us that for our function, it does not converge very well, except for right in the middle of the interval of convergence. Because let's look at this. If we look at -1 to 1, okay, looking at the interval -1 to 1, you can see that it does converge. We did figure out our interval of convergence to be -0.33 to -0.33. So we change the viewing window, the zooming window, so that our x values are from -0.33 to 0.33. So this is from -1/3 to 1/3. And you notice that actually in this area, it does not converge very well. I mean, they're pretty far off. Okay? The only place that it converges very nicely is in between our interval of convergence. So, and that's what we observed comparing the two graphs, that the interval of convergence for the base shows us that for our function, it does not converge very well except for right in the middle. So it does converge, just not very nicely. All right, why were the window settings -1/3 to 1/3? And that's because this is the true IOC for our function. Because remember, you notice here we only graphed what? We only graphed the first 5 numbers in the series. Okay, the first 5 parts in the series. So of course, the more that we graph, then probably the better our interval of convergence will look like. So this is the true interval of convergence if we were to graph this to infinity. All right, hope this helps. Enjoy.